Stop. Look at the wall behind your screen. It looks solid, it looks real, but more importantly, it looks like it's happening right now. You have a deep, intuitive belief that the past is locked. What happened 1 second ago is finished, stone cold, unchangeable. If a baseball breaks a window, you can't decide after the glass shatters that the ball actually went around the house instead. That's insane. That violates every law of logic you know. But what if I told you light doesn't care about your logic? There is an experiment, dreamt up by the genius John Wheeler and proven in actual labs, that suggests a particle of light can make a decision about its past, based on a choice you haven't made yet. A photon can travel for billions of years, crossing the universe, passing galaxies, deciding whether to be a wave or a particle. But it waits to finalize that decision until the very last nanosecond, right when it hits your eye. It implies that your observation now creates the history of the universe then. That sounds like magic. It sounds like science fiction. But it is standard, cold, hard quantum mechanics. Let me show you how you're rewriting the past right now. You live your life assuming time is a straight arrow. Think about this. Pick up a pen. Drop it. It hits the floor. Bang. That happened. It's in the past now. No matter what you do in the future, no matter if you cry, scream, or build a time machine, you cannot change the fact that the pen fell. The past is a library of books that have already been written, printed, and shelved. You can't edit the text. This is what we call causality. Cause comes before effect. The past determines the present, right? Wrong. Here's where your intuition fails you. This logic works for pens. It works for cars. It works for planets. But it does not work for light. When we zoom down to the quantum level, to the photon, the tiny packet of energy that allows you to see this video, the rules of the library don't apply. Close your eyes for a second. Imagine a photon traveling from a star to your eye. You imagine it like a little bullet, right? It leaves the star, travels through space, maybe bounces off a satellite, and hits your retina. Even if you didn't see it traveling, you know it took a specific path. It had a history. It was at point A, then point B, then point C. But quantum mechanics says something disturbing. It says that until you actually catch the photon at the end of the journey, it didn't take a specific path. It didn't take any path. It took every path. Hold that thought, because it's about to get weird. We aren't just saying we don't know where it was. We are saying it wasn't anywhere specific. The past of that photon is fuzzy. It is a cloud of probability, a ghost of maybe. And here is the kicker. The delayed choice experiment proves that what you do right now, at the finish line, forces the photon to go back in time and decide which path it took at the starting line. You are the editor of the book, rewriting the first chapter after you've already read the ending. How is that possible? To understand the impossible, we have to look at the most famous mystery in all of physics, the two doors. Before we break time, we have to break space. You've probably heard of the double slit experiment. Maybe you learned it in school and forgot it. Maybe you've seen a cartoon of it. Forget the cartoons. I want you to visualize this with me. Imagine a steel wall with two vertical slits cut into it. Behind that wall is a backstop, a screen that glows when something hits it. Now, imagine I hand you a machine gun. You spray bullets at the wall. Most hit the steel, but some pass through slit A and some pass through slit B. On the back screen, you get two stripes of bullet holes. This is simple. Things go through one hole or the other. This is how the world works. Now let's change the ammo. Instead of bullets, we use water. We push a wave toward the slits. The wave hits the wall. It splits. Two little baby waves come out the other side. One from slit A, one from slit B. They spread out. They overlap. Where the peak of one wave meets the peak of another, they get bigger. Where a peak meets a valley, they cancel out. They delete each other. On the back screen, you don't get two stripes. You get an interference pattern. Bright, dark, a barcode of energy. So far, so good. Bullets make two stripes, particles. Water makes a barcode, waves. Here is the part that keeps physicists up at night. We fire photons, particles of light. We turn down the power so low that only one single photon fires at a time. Click, silence. Click, silence. There is no way for this photon to bump into another photon. It is alone in the universe. It has to choose slit A or slit B. So we fire 1,000 of them, one by one. We go get a coffee. We come back to look at the screen. What do we see? Two stripes? Wrong. We see the barcode. We see the interference pattern. Wait, read that again. It shouldn't be possible. How can a single marble of light create a pattern that requires two waves overlapping? There is only one explanation. The single photon left the gun, became a wave of possibility, went through slit A and slit B at the exact same time, interfered with itself, and then decided where to land on the screen. It sounds insane. It sounds like I'm lying to you. But nature doesn't care what we find impossible. This implies the photon is a ghost. It has no location. It is everywhere at once. But here is the twist. This is the setup for the time travel trick. Scientists said, "Okay, you weird little ghost, I'm going to catch you." They put a sensor, a spy, right next to the slits. A tiny device that simply beeps if the photon goes through slit A or slit B. They want to know which path it took. They fire the photon again. The sensor beeps. It went through slit A. Great, we found it. But look at the back screen. The interference pattern? Gone. The barcode vanishes. Suddenly, you just have two boring stripes, exactly like the machine gun bullets. This is where your intuition fails completely. The moment you gathered information, the moment you knew the path, the photon stopped acting like a wave and snapped into acting like a boring little particle. It's as if the photon knew you were watching. If you don't look, it takes both paths, wave. If you do look, it takes one path, particle. So the act of measurement creates the reality. But John Wheeler looked at this and asked a dangerous question. What if we tricked the photon? What if we let it pass the slits as a ghost, but then decide to check its ID after it's already gone through? Can we force it to change its disguise in midair? Now let's break your intuition completely. You just saw that if we put a sensor at the slits, the photon stops acting like a ghost and acts like a bullet. This is the famous collapse of the wave function. People say it collapses because you touched it, but that's just a label. It's not an explanation. Think of it like a coin spinning on a table. While it's spinning, is it heads or tails? It's neither. It's a blur of both. It's in a state of superposition, a mix of heads and tails. But the moment you slap your hand down on it, whack, you force it to choose. It becomes heads or it becomes tails. The blur is gone. In quantum mechanics, the photon is that spinning coin. As long as we don't look at which slit it went through, it remains a blur. It remains a wave of possibility. But the moment we install a which-way detector, a device that tells us, hey, it went through the left slit, we slam our hand on the table. We force the universe to make a choice. The photon screams, okay, you caught me. I'm a particle now. I went through the left slit. And because it's now a single particle in a single location, it can't interfere with itself. It can't make the wave pattern. It just hits the back wall like a dumb rock. Two boring stripes. So here is the rule. Information destroys interference. If you know the path, you destroy the wave. If you don't know the path, you keep the wave. It sounds simple, but stop. What if we could erase the information? What if we let the sensor detect the photon, record the data, write it down in a computer, but then we delete the file before we look at the back screen? Would the interference pattern come back? This is the quantum eraser experiment. And the answer is yes. If you erase the which way information, if you destroy the knowledge of which path it took, the interference pattern reappears on the screen. It's as if the photon knew you were going to delete the data, so it stayed a wave. If you keep the information, the pattern vanishes. It becomes a particle. It implies that the universe doesn't care about atoms or forces. It cares about information. This leads us to the most terrifying realization of all. The photon doesn't make a decision when it hits the slit. It makes a decision when you make a measurement. But wait, what if we move the measurement? What if we let the photon pass the slits? Let it travel through empty space for a while, and then decide whether to check its path. Can we trick it? Can we let it go through both slits as a wave? Wait until it's halfway to the screen, and then suddenly yell, "Gotcha! Which path did you take?" Would it panic? Would it realize it made a mistake? Would it have to go back in time and change its decision? This is where John Wheeler walked into the room and dropped the bomb on physics. This is where the story pivots. The year is 1978. John Wheeler, a titan of 20th century physics, is staring at the double-slit experiment and thinking about time. He knows the rule. If you put detectors at the slits, the interference pattern disappears. The photon acts like a particle because you forced it to choose a path. If you take the detectors away, the interference pattern comes back. The photon acts like a wave because it took both paths. But Wheeler asked a question so simple it sounds stupid. What if we delay the choice? Imagine the photon leaves the light source. It approaches the slits. It has to decide, am I going through one slit like a particle, or am I going through both slits like a wave? Usually the experimental setup makes that decision for it. If there are detectors at the slits, the photon says, "Fine, I'm a particle." If there are no detectors, the photon says, "Cool, I'm a wave." But Wheeler said, let's trick it. Let's remove the detectors at the slits. Let the photon pass through the wall. Let it travel through open space for a while. Let it think it got away with being a wave. Then, at the very last second, after it has already passed the slits, we suddenly decide to measure which path it took. We force it to answer the question, which slit did you come from? This sounds impossible. The event, passing the slits, happened in the past. The photon is already halfway to the screen. If the photon passed through both slits as a wave, and then we suddenly ask, which one did you come from? The photon has a serious problem. It can't say both. That's not an allowed answer for a particle measurement. It has to say slit A or slit B. So, to answer our question, the photon would have to reach back into the past, erase the fact that it went through both slits, and rewrite history so that it only went through one. It would have to change an event that has already happened. Wheeler called this the delayed choice experiment. He wasn't suggesting magic. He was suggesting that the decision to be a wave or a particle isn't made at the slits. It's made when the measurement happens, even if the measurement happens after the slits. This implies that the past has no physical reality until it is recorded in the present. The photon doesn't have a history until you ask it for one. And if you think that's weird in a lad, wait until you see what happens when we scale this up to the size of the universe. Now let's zoom out, way out. Wheeler didn't just think about lab benches and slits in steel. He thought about the universe itself. Imagine a quasar, a super bright galactic core billions of light years away. It's blasting out photons like a cosmic fire hose. Between that quasar and Earth, there is a massive galaxy, a giant blob of stars and dark matter. According to Einstein's general relativity, gravity bends light, so the galaxy acts like a giant lens. Light from the quasar can go around the galaxy on the left side, or it can go around the galaxy on the right side. Sound familiar? It's the double-slit experiment, but on a scale that makes your brain hurt. Left path around the galaxy, right path around the galaxy. These two paths meet again at Earth. If we put a telescope on Earth and look at the quasar, we can see two images of it, one from the left path, one from the right. But here is the trick. We can choose how we observe this light. Option A. We can point our telescope directly at the two images. We can say, yes, that photon came from the left, that photon came from the right. We measure the path. In this case, the photon acts like a particle. It traveled billions of years along one specific route. Option B. We can combine the light from both paths. We can make them interfere with each other. We can look for an interference pattern. In this case, the photon acts like a wave. It traveled billions of years along both routes simultaneously. It went left and right around the galaxy. Here is the problem. The photon left the quasar billions of years ago, long before Earth had telescopes, long before humans existed, long before dinosaurs walked the Earth. It traveled through space for eons. It passed the galaxy millions of years ago. It made its choice, wave or particle, back then. Or did it? Wheeler argues that the photon waits. It travels across the universe in a state of suspended animation, a superposition of both paths. It waits until the very last second, when it hits our telescope in 2024. Then, and only then, does it decide what it did millions of years ago. If we choose to measure the path today, we force the photon to have taken only one route around the galaxy back in the Jurassic period. We rewrite cosmic history. If we choose to look for interference today, we force the photon to have taken both routes around the galaxy back in the Jurassic period. We rewrite cosmic history again. Think about what this implies. Our choice now determines what happened then. A decision made by a human in a lab in 2024 reaches back across time and space to dictate the behavior of a particle billions of years ago. It means the past is not fixed. The past is a cloud of probability that only becomes real when we observe it in the present. The universe is a participatory game. We are not just watching the movie, we are directing it. And we are editing scenes that were filmed before we were born. This was a thought experiment, a wild idea. But then we actually built it. We took this cosmic idea and shrank it down to a tabletop, and we proved Wheeler was right. You might say, well, that's a nice thought experiment, but can you actually do it? Yes. In the 21st century, we don't just think about things, we build them. We can't easily fly to a quasar and wait billions of years, so we simulate it. Enter the interferometer. Picture a laser. It fires a single photon at a half-silvered mirror. This is a beam splitter. Think of it like a fork in the road. There is a 50% chance the photon goes straight through, path A. There is a 50% chance the photon bounces off at a 90-degree angle, path B. This is our quasar around a galaxy moment. The photon has two paths. If we put detectors at the end of path A and path B, we can catch the photon. Click, it went path A. Click, it went path B. Particle behavior. No interference. But here is the trick. We can add a second beam splitter right before the detectors. This second beam splitter takes the two pairs and recombines them. It forces them to overlap. If the photon traveled both paths as a wave, the two waves will meet at this second beam splitter and interfere. Because we designed the paths perfectly equal in length, the waves will line up. Peak meets peak. Trough meets trough. Constructive interference. All the light goes to one detector. Let's call it detector 1. None goes to the other, detector 2. So, one beam splitter equals no interference, particle behavior. Two beam splitters equals interference, wave behavior. This is standard physics. But Wheeler said, wait. What if we decide to put that second beam splitter in after the photon has already passed the first one? The photon enters the maze. It passes the first fork in the road. It has to decide, am I a particle taking one path, or am I a wave taking both? It travels through the maze. while it is mid-flight, while it is screaming down the optical fiber, we flip a switch. We randomly decide to either insert the second beam splitter, force it to be a wave, remove the second beam splitter, force it to be a particle. We make this choice after the photon has already made its decision at the first fork. If the photon decided, I am a particle at the first fork, and then we insert the second beam splitter, it should get confused. It shouldn't show interference. It should just hit one detector or the other with 50-50 probability. If the photon decided, I am a wave at the first fork, and then we remove the second beam splitter, it should get confused. It should hit both detectors at once, impossible, or just one, particle behavior. So the photon has to know what we are going to do in the future. It has to know if we are going to put the second beam splitter in or not. But we don't know. We use a random number generator to decide at the very last nanosecond. Faster than light could travel back to tell the photon. We are trapping the photon in a logical paradox. We run the experiment, we fire the laser, we wait for the data, and the result is impossible. The data comes in and it is terrifying. Remember the setup. If we don't put in the second beam splitter, the photon should act like a particle. It should pick one path. If we do put in the second beam splitter, the photon should act like a wave. It should pick both paths and interfere. But we are making that choice at the very end. The photon has already passed the first fork. It has already committed to being a particle or a wave. So what does the photon do? Does it panic? Does it guess? No, it cheats. Every single time, without fail, the photon behaves exactly as if it knew our choice in advance. If we decide at the last nanosecond to remove the second beam splitter, the photon acts like a particle that took a single path all along. If we decide at the last nanosecond to insert the second beam splitter, the photon acts like a wave that took both paths all along. Think about what this means. The photon leaves the source. It reaches the first fork. It has to decide, left, right, or both. But it doesn't decide. It waits. It travels through the maze in a state of indecision, a ghost. Then, at the very end, we make our choice. We flip the switch, and instantly, faster than light, backward in time, the photon realizes what we did. Oh, they put the beam splitter in. Okay, guys, rewind the tape. We went through both paths. We were a wave the whole time. Or, oh, they took the beam splitter out. Okay, rewind. We only went through the left path. We were a particle the whole time. It implies that the photon's history, whether it was a wave or a particle at the beginning of the experiment, is determined by what we do at the end of the experiment. The future determines the past. This breaks everything. It breaks causality. It breaks the idea that time flows in one direction. The result is so bizarre that Wheeler himself said, "It is wrong to think of that past as already existing in all detail." The past has no existence except as it is recorded in the present. The photon didn't have a path until we measured it. It didn't have a history until we asked for one. And because we can change how we ask the question, we can change the answer it gives us about its own past. This isn't just a weird quirk of light. This is a fundamental property of the universe. And the implications for reality are staggering. Now we have a problem. The experiment works. We've done it 1,000 times. We've done it with light. We've done it with atoms. We've even done it with molecules. The result is always the same. The future choice, to measure or not, determines the past behavior, wave or particle. So how do we explain this without sounding crazy? There are two main interpretations, and both are terrifying. Option 1, retrocausality. This is the back to the future option. It suggests that information actually travels backward in time. When we make the measurement at the end, a signal goes back to the photon at the start and says, "Hey, be a wave," or "Hey, Be a particle. This violates everything we know about relativity. Cause must come before effect. If effect can come before cause, the universe is a loop, a paradox. Option 2, no reality until measured. This is the standard quantum mechanics view, the Copenhagen interpretation. It says the photon doesn't exist as a thing with a path until the moment it hits the detector. Before that moment, it is just a probability cloud. It has no history, it has no location, it is smeared. When we measure it, we force the universe to draw the photon into existence at that specific point. And because we forced it to exist now, we also forced it to have a history consistent with now. We create the past by observing the present. This is what Wheeler meant when he said, "The past has no existence except as it is recorded in the present." Think about that. The Big Bang, the dinosaurs, the Roman Empire, do they exist back there in a solid block of time? Or do they only exist because we have evidence for them now? If Wheeler is right, the past is a hazy fog of maybe until we look at a fossil or catch a photon from a distant star. We are constantly solidifying history by observing the universe. And this leads us to the final mind-bending conclusion. The universe isn't a machine running on its own. It requires a witness. So where does this leave us? John Wheeler looked at this quantum weirdness and came up with a phrase that should be tattooed on the forehead of every physicist. It from bit. It means that every particle, every field of force, even space-time itself, derives its function, its meaning, its very existence, entirely from apparatus-elicited answers to yes or no questions. Binary choices. Bits. The universe isn't made of atoms, it's made of information. And that information doesn't exist until someone asks for it. We used to think the universe was out there, a giant clockwork machine running whether we looked at it or not. Wheeler says no. He says we live in a participatory universe. We are not just passive observers sitting in an audience watching the cosmos unfold on stage. We are down on the stage. We are interacting with the actors. We are rewriting the script as we go, by looking at a star, by measuring an electron, by simply existing and interacting with the world. We are forcing the universe to make choices. We are collapsing wave functions. We are crystallizing reality out of the fog of possibility. We are building the past, moment by moment, from the future. This is the deep truth of quantum mechanics. It's not just about tiny particles doing weird things. It's about the nature of existence itself. The act of observation is an act of creation. You are not just a ghost in the machine. You are the machine's operator. So the next time you look up at the stars, remember this. That light traveled for millions of years, ghost-like and undecided, just waiting for you to look up. And in that moment, you didn't just see the universe. So, where does this leave us? John Wheeler looked at this quantum mess, this idea that our choices now dictate the reality of then, and he came up with a phrase that should be tattooed on the forehead of every physicist. It from bit. It sounds like computer code, and it is. It means that every particle, every field of force, every atom in your body, derives its very existence from answers to yes or no questions. Bits. The universe isn't made of stuff, it's made of information. And here is the kicker. That information doesn't exist until someone asks for it. We used to think the universe was out there, a giant clockwork machine, a movie playing on a screen whether we were watching or not. Wheeler says wrong. He says we live in a participatory universe. We are not sitting in the audience behind a glass wall. We are down on the stage. We are pushing the actors. We are rewriting the script in real time. By looking at a star, by measuring an electron, even by simply opening your eyes, you are forcing the universe to make choices. You are collapsing wave functions. You are crystallizing reality out of the fog of probability. You are building the past, moment by moment, from the future. This is the deep truth. The act of observation is an act of creation. You are not just a ghost in the machine. You are the machine's operator. So the next time you look up at the night sky, remember this. That photon traveled for millions of years, ghost-like and undecided, across the dark void, just waiting for you to look up. And in that exact moment, you didn't just see the universe, you finished creating it.